Hello, everyone. Welcome to a new virtual tour of the European Southern Observatory. My name is Hector, and I will be your guide today. I have been a member of the team of guides from Paranal Observatory since 2019. I joined them when I was doing my master's degree in Antofagasta, and I'm currently doing my PhD at the Leibniz Institute for Astrophysics in Potsdam, Germany. I work mostly with topics related with galaxies and the circumgalactic medium. Today I'm joined by Felipe, who will be your producer. Felipe, how are you?
Hi everyone. My name is Felipe Zurita. I'm an astronomer with a degree in astronomy, and I've been working in ESO for guiding the in La Silla Observatory in the past 9 years. Today I'm the producer. I show you the observatory Paranal, right? Through existing facilities and share some of the research and discovery where we are involved in. I hope you enjoyed the journey and the cosmos with us. So let's start in
Mhm.
Hector.
Yeah, and please, if you have any questions, comments, or greetings, just write it on the chat and we will display it at some point during the tour. So we're going to begin by telling you a little bit about ESO. So ESO, the European Southern Observatory, is an international organization that is comprised of 16 countries. And you can see them there on the screen. We have Denmark, Netherlands, United Kingdom, Ireland, Belgium, France, Portugal, Spain, Sweden, Finland, Germany, Poland, the Czech Republic, Austria, Switzerland, Italy. And we also have two non-European countries on the screen. We have Australia, who in the recent years joined as an strategic partner, and we have Chile. And Chile is the host country. The observatories from ESO, they are built in Chile. So during the 60s, ESO was looking for different places where to build observatories, specifically in the southern hemisphere, and Chile was trying to attract human capital to the country to to have more development. So Chile ended up offering the land, and ESO find the most suitable place to build the observatories. And the first one that they built was the La Silla Observatory. And in the image on the screen, you can see the different observation sites of ESO in Chile. So in La Silla Observatory, in La Serena region, in the north of Chile, we have the main telescope there is the ESO 3.6 meter telescope, and we also have the new technology telescope NTT. For the north, near the Changnam Plateau, we have two sites where we have Apex and ALMA. So Apex is an antenna that was a precursor of the technologies that were later used in ALMA. And ALMA is an international collaboration that is not only ESO. We also have North America and some countries from Asia Pacific. So ESO is just one of the members of these international collaborations. And closer to the coast in the same region, we have Armazones y Paranal. So in Armazones is currently being built the ELT, the extremely large telescope. And very close to that mountain, we have Paranal Mountain, and there we have the BLT, the Very Large Telescope, and his interferometry array, the BLTI. We also have a couple of surface telescopes, BST and VISTA, and in between the zones of Armazones and Paranal, we also have CTSUT, and this is an array of radio telescope that is focused mostly on detecting gamma rays. So this give us a bit of an idea of what is the landscape of the astronomy observatories from ESO in Chile. Now let's travel to our destination today, Paranal Observatory. So here we're virtually traveling across the Atacama Desert, and we are about 1600 kilometers north of Santiago, the capital of Chile. And more specifically, we are 130 kilometers south of Antofagasta, the regional capital, and the closest city is Taltal, which is 90 kilometers to the south of where we're going. Now we are advancing towards the summit of Cerro Paranal, which is at 2,600 meters above the sea level. This mountain is a part of the so-called Cordillera de la Costa, or the coastal mountain range. And here we are just 12 kilometers in a straight line to the ocean. So you may wonder, okay, can we see the Pacific Ocean in these images? Well, if you take a look at the background, there is a very hazy, blurry part with a lot of clouds. the Pacific Ocean is directly below those clouds. So if we're here in a desert, one of the driest deserts on the Earth, why do we have so many clouds in the background? Well, this is because of the Humboldt current. This is a mass of cool water that comes all the way from the Antarctic through the coast of Chile and Peru, and it produces an effect known as thermal inversion. And this phenomenon basically makes all the humidity to get stuck at about 1,100 meters. All the clouds are formed there. But here we're over 2,000 meters above sea level, and the coastal mountain range of Chile prevents this bad air for astronomy to enter deeper into the land. And we also have another natural barrier that makes this place ideal for astronomical observations. To the east, we have the Andes mountain range, that as this place has mountains that are above 6,000 meters high. And these mountains, they prevent the winds and high humidity coming from Argentina, Bolivia to enter this place. And the result is the very dry, deserted landscape that we have here. Now let's move a bit closer, and we can see here the top of Paranal Mountain. And we can see that the top was cut, a bill was rowed, and we have the different telescopes with a different name there. And I would like to mention to you that Paranal in the Quechua language means whirlwind. And this could be a reference to the whirlwind that sometimes occur in the desert because of the wind. But usually the air here is very calm. This is one of the best places on Earth for astronomical observation. And here in the middle of the Atacama Desert, we have an oasis full of life and full of science. So let's put ourselves together into the main platform of the Paranal Observatory. So here we are. And let's start by just taking a look around. So over here, we're looking toward the west. Here we see the clouds. Below those clouds is the Pacific Ocean. Then we can take a look at the south. You see this beautiful desert landscape. And now we're checking the east, and we have the Andes on the distance. And over here we have Volcan Yuyayaco, that is the border with Argentina. And here we have Cerro Armazones, the place where the ELT is being built. Now, the main telescope of Paranal Observatory is the BLT, but the BLT, the Very Large Telescope, is not just one telescope, it's an array of these four big telescopes that we have here. Each one of them has a primary mirror that is 8.2 meters in diameter. In addition to this, we also have some smaller telescopes, like this one over here. We have another one here, here, and over here. These are the auxiliary telescopes, or AT, and they have a primary mirror that is 1.8 meters in diameter, so about the size of a tall person. And as you can see, these different auxiliary telescopes, they are on top of tracks, and this is because they can move. And if you take a look here, we have these trapdoors. There are about 30 of those in this platform, and we can place them in any of those positions. So why do we need to do this? Well, because with Paranal Observatory, with the auxiliary telescope, they only work doing interferometry. The four big ones, they can also be used to do interferometry, or they can work independently. And we have a small animation to explain a little bit the concept of interferometry. So when we're doing interferometry, we're creating a virtual mirror. And we do this by combining the lights of the different telescopes. All the telescopes are observing the same object on the sky, and the light is conducted through underground tunnels into the central building, that is the interferometry building. The light is then combined, and this is done in an analog fashion. This is not a post-processing of the images. The light has analogically reached the same point. Okay, so why do we do this? Why do we gain by doing interferometry? We get mostly improvement on the resolution. The maximum separation where we're using the four big one and the four small one is at about 200 meters. And this 200-meter diameter virtual mirror gives us a resolution equivalent to an actual 200 diameter mirror telescope. But this only in terms of resolution. So what does this mean? This means that we can resolve two objects that are very close in the sky. With low resolution, we see them as a single object. With a high resolution, we can separate them. What we don't improve with this method is the amount of light that we can collect. So that is like putting a bucket on terrain. The larger your bucket, the more water you can collect. The larger your mirror, more light you can collect. And this means that you can see objects that are fainter. And they can be fainter because they are farther away or because they are intrinsically fainter. So if we want to see fainter and more fainter objects, we need to keep building larger telescopes, such as the ELT. Okay, so we're back at the platform here. So we have the primary telescope over here. We have UT1, UT2, UT3, and UT4, where UT stands for unit telescope. The four of them, they are the same on the inside, but they have different instruments. Each one has space for three different cameras or three different instruments. But besides that, they are completely identical. And in addition to this designation of UT1 to UT4, they were given names in the Mapudungun language. This is the language of the Mapuche people, which are natives of the southern part of Chile and also Argentina. And in that language, the names are Antu for UT1, and that means the sun. For UT2 is Cueyen, which means the moon. For UT3 is Melipal, which means something like 4 stars, and is actually a reference to the Southern Cross constellation. And finally, for UT4, we have Jepun, which means something like the star of the evening, and is a reference to the planet Venus. Now, we don't have time to go to inside of the 4 telescopes. We're only going to enter one, UT3, but as I already mentioned, they are identical in size, with the exception that they host different instruments. So we are entering here to UT3. And the first thing that you might notice is that it's very big, very big. So I have here some people on the sides that give us a sense of the scale. Here we are in what would be the 4th floor of the telescope. We have one of the instruments here, the other one is on the other side, and there is a third one below. And over here we have the primary mirror of the telescope. It's 8.2 meters in diameter, made out of a single piece. This is a monolithic mirror. It's 17 centimeters thick, and the top layer, and I'm talking about nanometers, is made out of aluminum, and that is what gives the reflectivity. These are among the largest mirrors ever built. We have some larger telescopes right now, but they use segmented mirrors that are comprised of many different parts. Now, we have the primary mirror over here. On top, we have the secondary mirror, and there is a third mirror that we cannot completely see in this image. Now, let's go below the telescope. This white structure, this white cell that supports the mirror, plus the mirror, weighs at about 22 tons. And over here, we can see these little gray boxes. These are the so-called actuators, and they are a part of what we call the active optic techniques. So the mirror is very heavy, and when we tilt the telescope to observe at a different point in the sky, the stress of the mirror can be very high. So the solution that people came up so that the mirror wouldn't break was to build it with a special material that has a certain degree of flexibility. This material is called zero dur. It's a mix of glass and ceramic. Now, the problem with this is that if your mirror is flexible, the curvature will not always be the same, and therefore you will not have always the same quality of images. So here come the actuators. So we have a system in place that is always measuring the curve of the mirror. And the actuators, which are like pistons, they can push or pull, they are always correcting the mirror so that the curve is always the same. That way we can guarantee the same quality of images. So this is the active optics, not to be confused with the adaptive optics. That is a technology to fight the effects of the atmosphere of the observation. I suppose everybody has seen the stars twinkle in the sky. Well, that is because light is crossing different layers of air that have different density, pressure, temperature, etc. And this makes the lights to turn into different directions. So the solution to contrast that is the adaptive optics, in which we use a known star in our field that we know how it should look on the images, so we can apply the necessary corrections. And if we don't have that, we use lasers, which shoot a very powerful laser up to a layer of sodium that is high in the atmosphere. These sodium atoms get excited and then they emit light. So we create a fake star. So let's go back on top. How does this work at night? Well, this telescope has two motions. This blue structure is the monitor of the telescope, and this whole part can be tilted. That's one motion. And the second motion is, as you can see here, this part of the floor is separated from the rest. This is because this part can rotate in 360 degrees. So combining those two motions, we can point at any place on the sky. But before we do that, we need to open the enclosure. And this part over here, that extends all the way over here, that is the part that opens to the sides. And we have a small animation showing how these work at night. So Felipe, thank you. So this is obviously exaggerated. We don't open the enclosure that much, but we open enough just to let the light come in. So the light will come from the sky. It will hit the primary mirror, that is a concave mirror, bounce, hit the secondary mirror, that is a convex mirror, and then it will go to the tertiary mirror. And this one can either send it to the right, or we can rotate it and send it to the left, or we can just let the light go straight down and reach the instrument at the bottom. So that way we can decide which instruments are we going to use for our observations. We can only use one instrument at a time. Okay, so we have a bit of an idea of how this telescope works. Do we have any questions so far, Felipe?
Let me see. We have a few viewers, but uh, they they don't leave any comments. I invite you, the viewers, to leave the comments, question anyone you know about the astronomy, the telescopes or astronomy, whatever you want about the stars, the cosmos. I invite you to comment in the chat books, or leave your readings about this presentation. So we have any things, but I have a question about the telescope.
Mm-hmm.
The common question is how far the telescope see in the sky.
Oh, that is a good question. And this will depend on different things. For one, the longer you observe, the farther away you can detect objects. So that's one of the things that's going to matter. And for some time, this telescope here apparently had the record to the most distant objects detected, but that record has longer been shattered, especially this year with the new discoveries from the James Webb Space Telescope. So I don't really have in my mind the farthest object that we have detected, but for some time we would detect the farthest object from these telescopes. That I do remember.
Usually, is for I think is for resolution. The resolution of the telescope determine how far and well can see the celestial objects.
Mhm.
But this is too complex to answer in one point.
Yeah, and we can also do interferometry here, so we can increase our resolution. So, and we with some programs that takes a really long observation time, we can go very far back. So that's also things to consider.
So I invite the viewers to leave comments and readings or whatever you want to know. So what is the next point? Meanwhile,
Okay, so next from here we're going to go to the control room, because at night nobody can be here inside the enclosure because everything needs to be completely dark. But before going, uh, I want to comment on how people clean the mirrors. That is something that people ask a lot in the in-present tours of Paranal Observatory. How do you clean the mirror? And there are two methods. One is Well, we tilted the mirror, and then an engineer gets on this crane and spray a carbon dioxide foam on the mirror, and it will just fall because of gravity, and it will drag any dust particles. This is done every other week, and it's a fairly simple and straightforward process. There is a much more complicated method, that is the recoating of the mirror. So for that, this entire white cells plus the mirror is taken from the telescope, and we use this list that we have over here, this yellow crane thing. We put it on a special truck, take it to the base camp, and then we remove the aluminum layer that gives the reflectivity to the mirror. And then on a different vacuum chamber, we put a new layer. This entire process takes about a whole week. During that week, there is no mirror in the telescope, so it cannot be used. And this is done every 18 months. And it's done one telescope at a time. So it's done once for UT1, then 18 months later will be for UT2, and so on and so on. Okay, so now we'll head to the control room. That is this building over here on the side of the mountain. So you can see it now from the side. In addition to the control rooms, in this building we also have some offices for the people that work here. And here we are inside of the control room. And you can see that there are a lot of computers, a lot of desks, a lot of chairs. And if you take a look at here, we have a plate that says UT4. That is because this area over here is only to control the UT4 telescope. Over here we have for UT1. Over here is for UT3 millipad, where we just were before. And over here we have for UT2. So here we're inside of this place, this console that controls the UT2 telescope. So we have a lot of computers, a lot of chairs. You may be thinking a lot of people work here at night, but that is not the case. Usually during the night, there will be only two people here. There will be an astronomer and a telescope operator. So these telescopes, they are very high tech and very expensive. So they don't trust astronomers with handling the telescopes. There is a job that is specifically to control and manipulate the telescopes. This is the job of the telescope operator. You can think of this as a plane with a pilot or a copilot, or maybe a rally car if you prefer that. So the astronomer, he's the co-pilot. He has the map of what we're going to do tonight, what are we going to observe, and the scientific reasons behind them. He's supervising the science. The telescope operator, he's the pilot. He's handling the machine. Okay, so if we have only two people here at night, why do we have so many computers? Well, you have to remember, each telescope has three instruments, and we want to have a dedicated computer for each of the instruments. We also want maybe have a dedicated computer to control and move the telescope. And we also need screens to display information, such as weather information. The climate here is usually very good. We have an average of over 300 clear nights during the year. But sometimes we can have some clouds or maybe too much winds, and this could be a problem. If the wind speed is too high and a small pebble is slipped up and it will to crash into one of the mirrors, that would be very bad. There are no replacements for the mirrors, and the mold that was used to build them no longer exists, so we could not replace them. So there are some operational limits regarding wind speeds, and as well as humidity and other things like that. Okay, so who can observe with this telescope and what do they have to do? Well, astronomers from any country of the world can use this telescope, not only countries that are member of ESO, and they have to apply for time. So there are a couple of times a year when astronomers they send their observation proposals. And these observation proposals they need to be very complete. They need to inform what wants to be studied and for what reason. They need to mention whether this object has been observed with other telescope before. They need to mention some operational parameters, like for instance, how far away we need to be from the moon so it doesn't disturb the quality of the observations? Or how much bad can the sky be that night? What we call the scene. What is the limiting scene that we need for this observation to be scientifically useful? And etc. and etc. And a committee reviewed these observational proposals, and they assigned time based only on the scientific merit of each proposal. And this is a highly competitive process. We received in Paranal Observatory more than 7 times observational proposals that time that we actually have to assign. So this is highly competitive. And some instruments are more competitive than others. Okay, so what's happened there? If you get lucky and you made a good proposal and it is accepted, then you can observe. And there are 2 observation modes. There is the service mode and the visitor mode. In the visitor mode, you get to travel here, you get to sit on the chair and supervise the observations. The drawback of this is, of course, well, you have to travel to Chile, but Chile is a very nice country to visit, so people usually like to do that. But if the night that you came here to the observatory, for some reason the weather is bad, well, this usually cannot be rescheduled. Then we have the service mode. In the service mode, the astronomer doesn't travel. He gives the instruction to an astronomer of the ESO staff, and they supervise the observations in his place or her place. In this case, there is a bit more leeway regarding rescheduling of observation, but again, this is not guaranteed. And the last thing that we can mention about this is that most of the time, the observations are done in the service mode. Okay, so once you have your observations, they are private for the astronomer that wrote the proposal for a period of about a year. They had the time to abandon their science and do their research. After that, everything is made public, and any astronomer can go into the ESO archive website, create an account, and download the data. But the objective of ESO is not just to create and control these observatories, it's also to promote the collaboration in the science and specifically in astronomy. So astronomy is a very collaborative science. So if you want to use observations that somebody else sent a proposal, what you will do is you will send an email, explain what you want to do with that data set, and people will usually agree and let you use it. And if they're very interested, they might request to be a part of your investigation. Okay, so this gives us an idea of how the science is done, but what are the science results? And we have a video showing the top 10 discoveries, not only with Paranal Observatory, but with all the telescopes and from all the different ESO observatories.
Yes, that's right. Let me show you the top 10.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that two other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Well, those were just a few of the amazing discoveries made through the ESO telescopes and the scientific stuff behind them. But we have an extra result, a bit of a bonus track. A team of astronomers captures the first image of a supermassive black hole. Please take a look. The Event Horizon Telescope, EST, an array of 8 ground-based telescopes distributed throughout the planet, coordinated by an international collaboration, achieved the first direct visual evidence of a supermassive black hole and its shadow. The image reveals the black hole at the center of Messier 87, a massive galaxy in the nearby Virgo galaxy cluster. This black hole is 55 million light-years from Earth and has a mass of 6.5 billion times that of the Sun. And there you have the image on the screen. Okay, I hope you enjoy our top 10 scientific discoveries. And I would like to remind everybody that there are, in addition to these virtual tours, there are in-person tours both of Paranal Observatory and La Silla Observatory every Saturday for Paranal Observatory, and for La Silla Observatory Saturdays and also Sunday, right, Felipe?
That's right. The Saturday and the Sunday is a day to visit La Silla and Paranal only in the Saturday, right?
Yeah. So for Paranal on Saturdays is there is one time at 10 in the morning and a second one at 2 p.m. These visits are completely free, but you need to register yourself in a website before, and you also need to arrive to the observatory by your own means. And in this visit, you get to see pretty much the same that we have shown here. But there's one thing that you cannot do during the in-person visit that we can show you in this virtual tour through the power of this virtual reality. That is showing you how this night sky looks from the main platform of Paranal Observatory. So the visits are only during the day because by night the observatory is working. But here we can show you this beautiful night sky. And here we are just not too far away from the sunset. You can see a bit of a glow from the sun over here. I want to start by showing you some of the wonders of the sky. Let's start with a very known constellation, Orion, the Hunter, that we have over here. So here we have Betelgeuse, the red giant star in Orion constellation that is supposed to explode as a supernova in the next hundreds of years or so. And it has given a couple of news recently because it has been changing its brightness. And people were wondering maybe it's going to explode today or tomorrow, but no, it was mostly some gas dust cloud that was passing in front of us that was making the star a bit dimmer. And over here we have the Orion's Bell, also as it's known in Latin America and Chile, Las Tres Marías, the Three Marys. And over here we have Orion's Sword, and here we have Orion Nebula. This is a star forming zone that we have over here. So in Greek mythology, Orion was a hunter, and at least in the version that I know, he was put on the sky by Artemis, the god of hunters, because Orion tried to hunt a deer that was sacred to Artemis, and he was put on the sky to fight all the animals that he has hunted on his life. So he's very close here to the bull, to Taurus. Here we have the bright star of Taurus, Aldebaran, and he's also being chased by the scorpion. And over here we have Sirius. This is the brightest star in the night sky that is part of the Canis Majoris constellation. And this is the hunting dog that was serving Orion. Now, if we go here near the horizon, we can see the Pleiades. This is an open star cluster that is a very beautiful object to look at, and is therefore one of the favorites of amateur astronomers. And or as it's called in other countries, in Japan, for instance, known as Subaru, and it's their logo of that brand of cars, actually. And now, if we look over here, we can see the spiral arm of the Milky Way, which is very impressive thing to look, and it's something that we can only look in this level of amazingness in the southern hemisphere. And over here we have these two cloudy things, where these are the Magellanic Clouds, and they are not clouds, they are satellite galaxies of our Milky Way. So we have the big Magellanic Cloud and the small Magellanic Cloud. And you can use them to try to find the southern direction. Unlike in this northern hemisphere, there isn't a bright polar star here, but we can take the two Magellanic Clouds and build a triangle. And here, in this position, that will be the southern celestial pole. And underneath beneath, the southern cardinal direction. That's one way of determining the south using the sky. We can also do it using the Southern Cross constellation, and the Southern Cross is over here. So we have the Southern Cross, and we take the large stick of the cross, and we extend it 1, 2, 3, 3.5, some people say 4 times, and then we reach the same point of the sky that is marking the southern celestial pole. And over here we also have Alpha and Beta Centauri, part of the Centaurus constellation, and Alpha Centauri, one of the closest stars to our planet. And lastly, we will finish this observation of the beautiful southern sky by telling you a little bit of the cosmovision that the natives of this area used to have. So for the Andean indigenous, uh, the Milky Way was a river, and different animals they will come to drink water from this river. So there will be a bird, a snake, and so many others. And the only one that I can recognize for myself is the llama. And here we have the llama. This is the head of the llama. We have the ears over here. This star is the eye of the llama. And at different times of the years, we can also see part of the body of the llama. So I hope you have enjoyed this gorgeous view of the southern sky as it is from the main platform of Paranal Observatory. But now it's time to return to today. And we're going to the next stop in our tour. So here we're at 2,600 meters above sea level, and we're going to go down to the base camp. The base camp is at 2,200 meters above sea level. Oh, I went to the wrong place. Sorry. I pressed the wrong button, but not to worry. Okay, now see. Yeah, over here. Now we are. And the base camp is a mini city in itself. Here we have everything we need to have the observatory running. We have some workshop when some pieces are being built or things are being repaired. We also have the buildings that are used to do the recording of the mirrors. We have an infirmary. We have our gym here because, well, people stay here for long periods of time, so they need to exercise. We have places for people to sleep. We also have our own power station here. When the observatory was first built, they were generating their own power. Then they were connected to the electrical grid of Chile. And the latest development is that the observatory is now using renewable energies. But we're heading now towards this place over here. This is the so-called Residencia. This is the place where the astronomers live while they are working here. Before we go inside, and this looks like it's sort of going underground, but it's not. The building is built using this slope of the mountain, and this building won some architectonic awards. But before we go inside, let's take a look at the landscape that we have here outside, because there's a very big contrast to what you will see on the inside. So here we have a beautiful deserted landscape, but that can be a little boring after a couple of moments. It's always the same colors. There is no variation. But when we go inside, we can see a lot of green. So why do we have so many plants here? It's not just because we have some good psychological effects of seeing green and having a lot of vegetation. This is also because of the pool that we have here. So the desert outside is very dry. So in order to have a higher humidity, we have a pool inside here, and this also allows us to have this tropical garden. And people actually can use this pool, and they can swim in them. And this building has 108 rooms. They are located towards the side. Here is the reception. There are also some offices. Over here is the cafeteria, where people eat breakfast, lunch, and dinner. There is also a game room, a library, a music room. Astronomers, and the engineers that work here at Paranal Observatory, they work by shifts. So they spend weeks, complete weeks here, and then maybe a week at home. So they need everything. They need to have a normal life here. Now, something else that we should mention here is that here at the center we have this curtain that is extended at night. I don't like the concepts that we usually have at our home that are to prevent the sunlight to come inside our homes. The objective of this curtain is to prevent the light from inside the building to leak outside. So that way we can turn on the lights inside this building at night without having contamination on our scientific observations. Okay, and as a bit of a trivia information, this building was used in a James Bond movie in Quantum of Solace with Daniel Craig. And it was the lair of the bad guy of that movie. Okay, and we are getting close to the end of our tour. Do we have any more questions, any comments, greetings?
Let me see. We have a greetings about on person. Thank you for the research and the wonderful photo of you post. An amazing place to rest after shift. Yes, it's the I think this is the best place to. And Carlos Diaz say, sadly I'm late for the stream and also have to go to studio. So I will see this video of a dinner becomes interesting. Yes, this is very interesting to know about the observatories of ESO in Chile.
Mhm. Yeah, and we also like to comment to everybody that is watching that you can always go to the ESO website, www.eso.org, and there you can find hundreds of videos, pictures that you can use completely free for whatever, for anything that you want to do for educational purposes or just to print a nice poster and put it on your wall. And you can also find this 360 tour and not only of this observatory and La Silla, and you can walk it at your own pace and rhythm. Uh, we are doing these virtual tours every Saturday. We are alternating between La Silla Observatory and Paranal Observatory, and also between Spanish and English. Please keep an eye on our social networks to know which one is the next one. I think it should be La Silla.
That's right.
Because,
The next one is La Silla in Spanish.
yeah.
So the next week, the next Saturday, we stay in La Silla to know about the origin of ISO in the region of Coquimbo.
Mhm.
So today don't have too much questions, but thank you for your greetings, the little few greetings we have. But thank you to you, Hector, to show the Paranal Observatory and the Residencia and everything have this wonderful place.
Yeah, and I would like to remind that in addition to these virtual tours, we'll also have in-person tours if you have the opportunity to travel to Chile. And again, they are completely free. You just need to sign up before, and you need to get to the observatory by your own means. But every weekend we have free tours at both La Silla and Paranal Observatory. And also, if you know anybody that might like this type of content, please let them know so they can be part of the next virtual tour. And
So
I think,
this is all for today,
mhm,
and see you in the next week. For my part,
yeah,
I say goodbye to everyone and see you in the next Saturday in La Silla. And you Hector.
yeah, it was my pleasure to be your guide today. Please have a very nice weekend, and we'll see you on the next occasion. Bye.
So goodbye.